Okay, this video is going to help you answer questions 1 through 4. So our focus question for this week is, how are transverse and longitudinal waves alike and how are they different? So you've learned what a wave is. It's a disturbance caused by a vibration. You've learned what the properties of a wave are. A wave has amplitude, frequency, wavelength, and wave speed. And you've learned how to measure a wave. And you've also learned the relationships between amplitude and energy and frequency and wavelength. The more energy there is, the higher the amplitude, the higher the frequency, the shorter the wavelength, the lower the frequency, the longer the wavelength. And so this week, we're going to look at how transverse and longitudinal waves are alike and how they're different. So, which do you think travels faster, light or sound? So we've seen this video before, and we know that light travels faster than sound. We can see the light flash before you hear the thunder. In a baseball game, you will see the bat hit the ball before you actually can hear it. You'll see the fireworks in the sky before you can hear their boom. Light travels faster than sound. Can you think of possible reasons why this might be the case? Well, one reason that sound and light travel differently is because they're carried by different kinds of waves. So, transverse waves, we've learned that travel perpendicular to the direction the energy is traveling. So while the energy is traveling from left to right in the video, the actual wave travels up and down while that energy is going from left to right. So the particles move up and down. Now, an example of a transverse wave is going to be light. And I think next week we're going to start talking more about light waves. Okay. So remember, the particles don't actually move anywhere. They only vibrate and then they return to their original position. And if you look in the little diagram here at the bottom and you focus just on like one little particle, so let's focus on this one where my arrow is. You can see the particle is just moving up and down, up and down. It's not moving left to right. And so that's what a transverse wave is. The particles move up and down while the wave, the energy goes from left to right. Okay. Now, longitudinal waves are different. So waves, a longitudinal wave does still carry energy, but it carries it differently. Instead of the particles going up and down, the particles are parallel. So in the video, you can see that the hand gave the slinky some energy, okay? And that energy is going from left to right, and so are the particles. So longitudinal waves move the particles of the medium parallel to the direction in which the waves are traveling. Now, the coils in the spring will move back and forth. So watch this again. And if I'm see how they're moving back and forth? And let me pause it right there. Okay. And we've talked about this already too. Now, where the coils are close together, okay, see where these coils are kind of close together? We call those compressions. And then where the coils are spread apart, so right here between the two compressions, those are called rarefactions. Okay. Sound waves are examples of longitudinal waves. Okay. So here we have another model of a longitudinal wave. And if you remember, we can easily draw a transverse wave. It kind of just looks like a snake, okay? But to draw a longitudinal wave, I want you to think of these compressions, okay, these compressions right here, as being similar to the crest of a transverse wave. And I want you to think of the rarefactions as being similar to a trough. And if we can equate those two variables, then we can draw a longitudinal wave just like a transverse wave. We just need to know the difference in how the particles move. Okay. So if you look up here, I like this simulation because you can see they highlighted a particle. See this red particle here? And while it looks like the red those dots are moving left or right, they're really not. Just focus on that red particle. The energy just moves it slightly forward and then it's going to go back to its resting position. And so this validates that waves transfer energy, not matter. Remember, matter is a solid, a liquid, or a gas. Okay, so let's go back to talking about these rarefactions and these compressions. It's really hard to draw a longitudinal wave. This is really difficult. So if we equate a compression to a crest and a rarefaction to a trough, then we can draw longitudinal waves very easily. Okay, and I'm going to show you that on the next page. So here we go. So here's that model on the previous slide, frozen. And if this is a compression and it's equivalent to a crest, look how those match up. And this is a rarefaction and it's equivalent to a trough, look how that matches up. So I can translate this longitudinal wave into a drawing so that I can easily understand its properties. I hope that makes sense. Okay. So here what we have is the amplitude. So just like a transverse wave, longitudinal waves have an amplitude. And amplitude is a measure of how compressed or rarefied the medium becomes. So if you look at this picture right here, you can see this is compressed. See, this is compressed here. Compared to this picture, these particles are really compressed. This model represents a low amplitude because those particles are not that compressed together. So low amplitude means less compression and less energy. But then if you look at this model, the particles get really, really close together. They're really compressed. So this model has a higher amplitude, higher pressure, more energy. Okay. So high energy vibrations can cause compressions to be very crowded, as you can see in the pictures. This will make the rarefactions loose. So you can see how the particles in both models, those rarefactions, they're kind of loose and spread apart. Okay, wavelength. So a wave travels a certain distance before it starts to repeat. We learned this in a previous lesson. The distance between two corresponding parts of a wave is called its wavelength. And we learn in a transverse wave that the crest to a crest or a trough to trough is its wavelength. Okay. Well, in a longitudinal wave, the wavelength is from compression to compression. But remember, we can translate this wave into a transverse wave. So if this compression is the same as a crest, look, I can draw this, okay? And then if the rarefaction is the same as a trough, I can draw this, and then I can draw this wave right here, which matches up with this. And so I can measure my wavelength a little bit easier. But if you can easily see this, you can draw the wavelength here as well, or measure the wavelength here as well pretty easily. Now, frequency and speed are the same thing for both transverse and longitudinal waves. So wave frequency is the number of complete waves that pass a given point in a certain amount of time. We're going to look at a video in a second that I think might help you understand what that looks like in a longitudinal wave. And then remember, frequency is measured in units called hertz. It has to be a capital H and a lowercase z. In the last lesson, a lot of you were putting a lowercase h, and that is incorrect. Okay. And the speed of a wave is how far the wave travels in a unit of time or distance divided by time. And really, we're not really worried about you understanding speed at this point. What you need to know are the relationships between amplitude and energy, and then frequency and wavelength. Okay, so we're going to watch a video here. And I'm going to let him talk, and I might try to talk over him. Oh, why won't you play? Whoa. Okay, I embedded it. Okay, there it goes. Let's try that again. There it goes. Okay.
Hi guys, today I just want to show you a demonstration of transverse and longitudinal waves using a slinky. Now, transverse waves, the direction of energy is going to be going forwards, and that's the same with longitudinal waves as well. The energy
Are you joking me?
is going to go this way, but with a transverse wave, the medium, so in our case the slinky, which is what the wave is going to travel through, is going to be moving perpendicular to the direction of energy transfer. So let me give this a go.
So that's a transverse wave.
So you can see the pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Now another kind of wave is a longitudinal wave. Now with a longitudinal wave, the medium, again, which is the slinky, moves in the same direction as the energy transfer. So the energy is moving in this direction. Our wave is going to be, or the medium, the slinky, is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave.
See the compressions there?
So in this case, you can see that there's a part where the wave gets compressed and a part where the wave gets rarefied. And that these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave, like that. That's a transverse wave. Okay, bye for now.
Okay. So let's talk about how transverse waves and longitudinal waves are the same, okay? So the first thing, both are repeating patterns with similar properties. Both waves have wavelength, amplitude, and frequency. The relationships between the properties are the same. So a higher energy means a higher amplitude. A low energy means a low amplitude. Frequency and wavelength are inversely related, and then vice versa. So if frequency is increased, then the wavelength will be short. And if frequency is decreased, then the wavelength is going to get really long. Okay. And that's true for both of these types of waves. Both kinds of waves transfer energy, not matter. And both occur when there's a disturbance caused by a vibration. So those are the similarities. That's how they're both alike. Now, there are some differences. So let's look at those. So in a transverse wave, energy in a transverse wave, the particles of the matter vibrate across that center line. They vibrate perpendicular to the direction of energy transfer. But in a longitudinal wave, the particles vibrate parallel to the direction. And if this is still confusing to you, go back a slide and watch that video again and watch the way he moves the slinky for a transverse wave versus a longitudinal wave. In a transverse wave, we call the wave when it travels in the form of crests and troughs. So when the wave moves up above that resting position, the top of the wave is called the crest. And when it moves below that resting position, it's called the trough. In a longitudinal wave, though, the wave travels in the form of compressions and refractions. So it's traveling left to right. And those particles, when they're really close together, we call those compressions. And when the particles are far apart, we call those refractions. And then finally, amplitude in a transverse wave is measured from the center line to the crest or the center line to the trough. But in a longitudinal wave, amplitude is measured by the degree of compression or how close those particles are. And so this wraps up the video for questions 1 through 4. Use this to answer those questions. And then if you need to come back and watch the video again. If you're struggling, hope this helps.